right, thanks for coming to our talk. This is Genetic Malware, or Designing Payloads for Specific Targets. A little bit about us. My name is Morrow, and I've been doing InfoSec for approximately 11 years. Started out at Booz Allen Hamilton. No, I was not lucky enough to be in Hawaii, and no snow. First question everyone gives me. But I did meet this guy, which was a good thing. I better than snow. Naturally, no. And so at Booz Allen, I did a lot of blue teaming, as well as SecOps, forensics, pen testing for government agencies, those sorts of things. Then I moved on to Amazon, where I was responsible for packing pretty much everything except for Kindle and AWS. Good times. And currently I'm at a cloud startup doing cloudy pen test or web application pen test, depending on who you ask, and focusing on mobile stuff as well.
I am Josh Pitts. My InfoSec claim to fame is backdoor factory via proxy, which led to finding the Russians patching stuff over Tor, right? But that's like being famous in InfoSec, it's like winning the AtoSec contest. But I got started in InfoSec in 1998 after I joined the Marines, worked in SIGINT, and I got injured after going to jump school. 2 days later, SEER school, which I call the Get Mo experience. And then I went to recon school a couple days after that, got stress fractures, was out behind the desk for a year, and they're like, we're going to make you a terminal area security officer. I was like, all right, what am I securing? Oh, well, we have 311 windows and Banyan Vines. I'm like, all right, awesome. So I do AppSec, red teaming, web testing. I work with this guy, and so we're doing some SecOps testing and everything. So how did we get here? Well, we were drinking coffee one day, which we do a lot of. Hold on. Hold on. Oh, there we go. And I turned and looked and I said, dude, I got this one-time pad compression encryption thing. I can use a binary to compress another binary. And we can deploy a DRM or malware with it. Let's submit the Infiltrate and do some research and write some code. And, he was like, awesome, let's do it. And so here we are. So if you write malware or, conduct operations, you have 4 enemies besides law enforcement. And these are basically who they are, pretty high level. And the first one is antivirus. And now, antivirus was founded by the Charlie Sheen of our industry. I mean, why do people still talk to this guy? It's just because he's just fucking ridiculous. So, if you're in this room and you're conducting operations, AD is not a problem. In fact, you probably own the domain because of AD. It's like, hey, thanks. So I do have I do have a respect for F-Secure because they look fairly independent, and Kaspersky because, I don't want them to kill me. So,
And they have a botnet.
And they run the largest threat intel botnet in the world. So now there's these online sandboxes, right? And I've been uploading programs to online sandboxes for a couple of years now. And when I mean programs, I mean malware. And what I mean by uploading, I mean fingerprinting. And so a lot of these sandboxes, they implement these stupid triggers or simple triggers, right? I mean, there are sandboxes that put the hash of the sample in the environment variable. So sometimes I want to put Stuxnet sample, MD5 in the environment variable just to mess with people. But no, you can actually bypass these automated sandboxes really easy because they are pretty predictable and not very creative. So yeah, you can identify antivirus IP space, researchers, where they're coming from. It's just really great kind of hobby to have. Now, the reverse engineer, the way I like to think of the reverse engineers, they are the apex predator when it comes to malware. If your entire payload executes in memory at some point, the reverse engineer can figure it out, right? But if you insert a step into the process where you can slow the reverse engineer down, you're conducting operations, they give you time. But if you can insert a step where they become a password cracker, then you really start pissing people off. It's kind of fun. So, and then this leads to crowdsourcing, threat sharing, info sharing, threat bot. And I really think this is a giant game of whack-a-mole, the malware must die folks they just love just hitting the same thing over and over again. So if you can defeat and reverse engineer, the outcome of this is less effective. Like, we're going to go into that, and you're going to see that. So how are we going to do this? Well, enter environmental keying, right? And we're going to have a short primer that covers 18 years of research. So put your seatbelt on.
5 minutes.
Like 5 minutes. So clueless agents. This is the first paper, came out in 1998 by Schneider. Phenomenal paper. This is, I think, the best paper on the subject because it's readable, because I'm not very bright. And they make everything very easy to understand. Now, of course, since it's academic, there's no POC. So then you have secure triggers by Core in 2003. They were like, screw clueless agents, we're not even reference it. They talk about defeating reverse engineers and analysis, and they make a mention of OTP, and then they have some PhD level wizardry math that I was just like, I was in the Marines. But it was really good. It was really, really good. Okay, so, but again, no POC, so I don't know if they sold the product, if they weaponized it, or what they did, I have no idea. It just went into the ether. So the Bradley virus, this is a really great paper. He talks about encrypted enclaves, one payload decrypts another payload while looking at other keys. Really good. And he had some quotes in there that are great. We don't have the complete source code. So I think some of this is science fiction. I mean, if you don't release code or you're not selling a product, then basically I think you're just doing science fiction. So yeah, he had some ethical concerns, so he didn't release anything. So no POC. Now, remember the guy's name? It's like Fivioli or something? Just remember that name, because it's going to come up again. So, Nate Lawson, this is a great blog post on using secure triggers in gaming. So, like, you get to a certain point in the game, and then you get all these trinkets or whatever, and then you decrypt the next part of the game, which is, a great idea. Of course, it's a blog post, and there was no POC again. So then you have the Uber malware in 2008, which has the guy from the Bradley virus. So they talk about using OTP, plausible deniability, but their sample was really small. They used a bash script against another bash script with the key was like not even 1,000 bytes, which was kind of cool. I mean, it was a Zor, but again, there was no POC. Same guy did the Bradley virus, like ethical concerns. And then another paper in 2012, they just rediscovered everything. They didn't reference anything before them. They didn't even do Thomas, the clueless agents, or the Bradley virus. They talked about environmental keying, and they had some very good quotes. Due to time constraints, exceeds the scope of the paper. At the inception of this paper, concerns were raised, and so of course they had no POC either. So you're telling me 18 years of research, no POC, nobody, no open source POC. People develop products. But no open source POC, so people could mess around with and deploy on networks. Nothing. But we have the flashback in 2011. Now this was only OS X. The way it worked is it would go and it had a scout agent that would get the UUID, and then it would upload it to a server, encrypt the payload based on the UUID, and then send it down back to the user, execute. The problem was it got caught because it didn't use any variability. But it took several months before this entire campaign, and we're talking thousands of maps, hundreds of thousands, 10,000 or something, infected. But I think the downfall was mass infection, and they didn't change any of their operations, right? And then Gauss. Who here remembers Gauss? There's like 4 hands. Yeah. So this was discovered by Kaspersky. Now, there's an encrypted payload named Godel, right? I don't even know if I'm pronouncing that right. But what it did, it took an environment variable for the program files, and it hashed took an MD5 hash of that 10,000 times, and then that was the key. And Kaspersky got this, and they said, you know what, we need help with this. They told the community, we need help. Now, to this date, no one's come out and said, we did it. Now, somebody knows how to do it, but they haven't come out and said, yeah, we did it. And so I would call this a very successful operation, because I'm sure the operation is over by now. It's been 4 years. But who knows what that was hiding. It could have been another C2, could have been more malware, hidden C2, who knows. But I'm going to say it was successful. So let's talk about malware compared to biological and chemical agents, right? So chemical agents, they're area effect weapons. And the reason I'm bringing this up is because let's try to design malware or at least targeted malware, to work in effect with, like chemical agents or biological agents. So with chemical weapons, they're effective for even days and weeks, depending on the weather. Now, you could make malware that only executes when the local weather is 80 degrees, like it reaches out and checks weather.com or something stupid. You could do that, but that's just dumb. But how would you do that? You would target certain specific environment variables. You could have it check system time right. You can have it like good for a year, good for a month, good for a day, depending on how you want to do it. And you can check your external IP address. Of course, anytime you reach out to the web to get any kind of IP address, that's an indicator compromise. But if you're good about it, and use common addresses, it's really not that big a deal. Now, biological. Now we think about viral. We're not going to make anything that spreads, right? We're doing something very targeted. So Wikipedia has this article, and these things like genetic targeting is called like ethnic weapons, and that's where you target what something is versus what just a general kind of thing. Like how would you do that in computers? You have path, right? And then you could actually use a particular file, a version of a file. So you get very specific, or even a location and a version of a file. So you get very specific to what you want to do. Now, how would this work in operations? Well, the idea is you could deploy everywhere and work somewhere. So you could actually do a mass infection campaign, but you only infect like 4 hosts, right? Because you're looking for very specific things. And then you can have operational plausible deniability. This is an idea if you have a very big shop, like in China, or you have a very big shop of operators, and you want to be able to distribute agents or malware to be deployed to their clients that they are in charge of, or their bots that they're in charge of, and they can't even reverse engineer what the agents are for, right? So if they were to leak these things, nobody can reverse engineer these things until they're on the target. So that's kind of the idea. And also, I kind of touched on this earlier, you can have a hidden command and control. So you can have, and this is the idea. So you have your first deployment command and control. Let's say you're after 4 computers in the world. They're very specific, but you decide to infect all the things. You're like putting backdoors in cracked games. You're just going, you don't care. You're infecting everything. So eventually you get one of your computers, but all the AEDs are flagging your initial loader and your command and control. So you're like, all right, well, we're going to stand up a new one because we can do that. And then you get more computers. And then you're infecting more folks. You get caught again. Same thing. You keep going until you get all 4 computers eventually. Now, that's kind of the idea. Now, what would happen if somebody released a POC and more of the world started using targeted malware? What would happen? Would it be an apocalypse? Right? I don't think so. I really don't think so. I think some defenders might be upset initially, right? They're going to have to figure out a way to. They don't realize they're given a great gift, right? Because they can figure out a way to defeat this stuff, and then they can sell more stuff. Right? So Travis is going to take over our implementation.
All right, so like Josh was saying, absolutely, we can do some really great stuff with our tool, and our tool is called Ebola, which stands for Ethnic Bioweapons Limited Access. Ethnic because it targets a subset of companies based on a group attribute, and bio because it is like your deployment can change based on attributes, just similar to biological weapons and pathogens in the wild, and limited access because our goal is to make it more difficult for the reverse engineer or sandboxes and those sorts of things, automated technologies, to be able to get to your actual payload. So, kind of what it is we're doing, right? Always, as an attacker, we're looking for a better way in. The Greeks did that at Troy, and we're doing that on your network. And it hasn't changed, since the beginning of time, right? So, what we've devised is a way to protect and deliver your payload to the right company at the right time, on the right system. And most importantly, we keep your payload safe. So while our loader may eventually get flagged, your payload, unless it is the right system at the right time, will not actually get caught. a little bit about Ebola. So we support 32 and 64-bit DLLs, executables, Python scripts, as well as straight shell code. And our protection mechanisms we support currently are symmetric environmental variables, we'll discuss in a minute, as well as a single file, and we support one-time pads. And the outputs, we have a Python loader and a Go loader that can get deployed to client environments. A little bit about the framework. So we decided on a Python-based templating framework. So everything is modular, so that as we build new features, new functionality, and new languages we support, we can drop them in here and be able to use our builder. In order to get started, you use Ebola.py, you supply your attacker payload, and you set up a genetic config. We'll go over that a little bit about all that goes into that. Next is the encryption folder. Once we've parsed your config file, we jump into the encryption folder, and this is where, based on whether you're doing symmetric encryption or you're doing a one-time pad, this is our loading script. This takes in all of your configuration options. Are you looking for, an IP range? Are you looking for all different paths? Or are you looking for a file? And we go through and parse, and we use these templates. So as you can see, we support Go and Python now. If we supported, say, Ruby
Or C.
then it would be just another folder in here, and we template everything out so that our current building script would work with all that. So we're going to cover the Go flow, but it's almost exactly the same for Python. And as you can see here, we have, as I was saying, everything broken out. External IPs, system paths, system times. So you can just drop new things in here, and you can easily update the framework for what you're doing. So within the payloads section is how we load things in memory. So if we come up with or find new ways to load things in memory, we can add a new payload. Right now we support memory module and shellcode loading directly with Go. So we discussed a little about the framework. Now on to our protection mechanisms for symmetric. First off, we're going to start with environmental factors. This is going to be anything you have on the Windows system that's customer-defined or user-defined, such as base stuff like username. But if you had some Oracle-specific things, some Java-specific environment variables, we can target as many of those as you want, as well as a file system path or specific application. External IP range based on octets, as well as a time trigger. So how we build this key is we take all these factors together, and you'll notice there's a repeating pattern here, a theme. We always have a payload hash. This is your payload that you've provided to us. And if you notice, we have an offset bytes. This is user configurable as well, so that when a defender has your malware and they're looking at this, they can't just hit virus total and say, hey, what's the indicator of compromise for this payload? Also, even if it's not on virus total, they can't search the network if you were to drop this to the disk. They can't be searching the network for this indicator compromise item. And the way we create the key is we do a SHA-512 of the combination of every single one of those environment variables, times as many iterations as you want. Again, if you do one, pretty fast. If you do 10 million, it's going to take a really long time on the client side for every single key.
On this Mac, it takes about 10 seconds for one guess.
Yeah.
So
10 million is not a good idea, but it's going to be on your appetite for time-based spending. And so we're going to take the first 32 bytes, and that is going to be our key. We're going to encrypt that payload, the one that you provided us. We're going to compress it so that we're trying to get some space savings here. It's hit or miss in terms of whether it'll be the same size or a little larger. And we're going to base64 encode that blob, and that's going to be inside of our loader. So on the decryption, it's a similar process. We're going to go backwards. We're going to retrieve all the environment variables you specified. We're going to traverse the file system from whatever starting point you want. So if you say C, it's going to take a lot longer than if you're closer to, say, C program files or C Windows to what you're looking for. Again, this is a time trade-off for how long you want it to run on the client system before your payload executes or before it gives up.
Right.
So that's going to be up to you. And we're going to combine every single possible combination as we iterate through the file system. And we're going to create a key. We're going to attempt to decrypt our payload. We're going to check the hash. If the hash hashes match, then we go ahead and execute memory. Otherwise, we continue on to the whole file system. And if nothing's found, we exit, not our system. Now on to unique files. So this picture pretty much describes what we are doing. We're going to use the payload hash we discussed earlier, and in the location, we're going to do a random location within the unique key file, and we just added a feature that's configurable in terms of an offset. So we have a max size so that this is not an indicator for a defender as to how large the file is. Because if your location of the file you're using was really large, then that's going to be an indicator they only have 10 or 20 files in an entire network that's, say, 150 megs or something like that. So we limited that down as user configurable so that it's not a major indicator for your operation. And again, we create the key. We do a SHA-512 of the random bytes we read, and times however many iterations you want. And we take that, we compress it, and base64 encode it, and drop it into the loader. Decryption, same process. We're going to traverse the file system. We're going to create a key from every single file we encounter. And we're going to attempt the decryption. If it works, execute. If not, move on. So we just finished up with symmetric protection mechanisms, and now we're going to look at our one-time pad or OTP protection mechanisms. One-time pad, I really like this one. This is probably my favorite one because you take from a known good binary on anyone's system and you recreate your malware. I just think it's really cool. The way we do it is we use an offset table. So we look through the known good binary that you provided from a client system, and we're going to hope to find the largest amount of bytes possible that match our attacker's payload. And we're going to rebuild that based on that offset table, the actual attacker's payload from the good payload. So the way we create this is we actually have the regular payload hash. We have a 10% match. The reason for this is when you're running through the file system, you're going to have a lot of files. Some of them will be really large. And the way our methodology is doing this is we're rebuilding all of these. And if we do 10%, then we have a huge time savings of rebuilding 100% before we realize it's a failure. So that's our idea with this short length, is it's just another hash, but we're only doing a 10% hash to check, so that we speed up the process, but not so much that it's ridiculously easy for a defender to do this across our whole network. And again, we build a lookup table, and this is actually what is being compressed and inside of the payload, and this is where, depending on how large of an offset you look for. So there's a time trade-off here on the attacker side. When you're building this payload, if you choose, you want to look for, say, 24 bytes, right? You'll spend a long, long time building that table. But if you say 8 bytes, you may spend, what, 10 minutes or so building the table on your side. But the larger the bytes, the smaller the size. So if you choose 8 bytes, seems to be a pretty good number, you'll actually save some space from your original size, which is kind of neat. And again, this is how we actually build the table. So you see on the attacker side, we have our payload. We're looking for these 3 bytes. We found them over here in the target binary. And we'll actually add them to the offset table. We'll build the entire binary out, and this is what actually gets sent over. So if someone's looking at this, this is largely useless to them because it is just a lookup table of bytes and addresses. So as I was saying, the way we decrypt it is similar. We go through the entire file system. We're going to open each and every file. We're going to read it. We're going to build 10%. And then we're going to validate. If it validates 10%, we build 100%. And we check again, and we load. So our outputs, aka cyber pathogens, if you're the FBI, it's even worse on phones, are Go and Python. So right now our loaders support a Go loader and a Python loader, which the Go loader and the Python loader will both have your encrypted or protected payload inside of it, and it will do all of the operations we've discussed. And this is why we did templating, so that we can add additional outputs in the future as well. So compatibility. We've had some issues with the Python DLL loading, specifically with Metasploit.
Well, across operating systems, it was ugly.
Yeah.
So we're not including that.
Yeah. So yeah, we had some mixed results, and so right now we're we're not supporting that. But on the Go side of things, you can do pretty much everything in memory. We support reflective DLLs, regular DLLs, executables, and shellcodes that never touch disk. They all go directly into memory, which is awesome. So you can use stuff that AV would normally flag on, and it will not get hit when it doesn't, because it never drops the disk.
Yeah, and we learned about this at ShmooCon. I mean, I knew about memory loader, but this hacker named Virus gave a talk on Go and memory module, and it changed my life. So we included it. Yeah, that's pretty good. So.
And we want to Josh for the usage and the bullet I can.
All right, so this is how you use it. That's pretty much it. We're done. No. So you roll it up high payload, and then you change the config file depending on what you want to do. So let's talk about the config file. There's 3 sections. You have an overall section, which basically says, I want to go this route. It's like choose your own adventure books. I grew up during that time. It was the original sucky RPG. And then you have your OTP, the one-time pad settings, and then your symmetric settings. So the overall section, so you either pick OTP or environmental, okay? And then you have Python, Go, or both. Now, if you're doing a DLL and you pick both, it's going to error out because we don't support DLL. So
For Python.
Yeah, for Python. Now, we do have a misprint on our slides. We do say DLL x86, but that's wrong. I didn't update the slides. And then you can pick the number of key iterations. So again, if you do 10 million, it's going to take you forever. But then again, they're one guess every 10 seconds. It's going to take them forever to try to guess your key, right? So for the one-time pad settings, again, you can pick full. So that means you're going to make a lookup table, or key, which we find a random location within a file, a random link that's at least a certain length. We pick a fairly large key, and then that's going to be somewhere in that file. So the pad, so you can set, it can be anything you want. So a target, like it can be, you can say, I only want to execute on machines that have McAfee at this version, or BitTorrent, or Bitcoin, or whatever you want to do. And then scan directory, so you can actually use a fixed path, or you can use an environment variable like app data, program files, system, whatever. And then byte width, and this is the matching for the one-time pad. So if you want to try to match at 15 bytes, it will go 15. If I didn't find 15 for this length, then I'll go 14 until it finds a match all the way down to 1. So if you're using a pad, make sure at least all 256 bytes are in that pad, or it will never work. Just keep that in mind. So you want a fairly large pad. Well, you don't need a fairly large pad, but a larger pad is better.
Not a text file.
Yeah, no text file. And so pad max, I left that out, but so we support up to a 16-byte pad. So what it will do, let's say you have a 4 gig file or a 4 gig whatever you're going to use for the pad. It'll just take the first 16 bytes. Megabytes, yeah, sorry, megabytes. And we did that because for compression reasons with the lookup table. So the symmetric key settings, there are 4 sections: environment variables, path, IP ranges, and system time. So the environment variables, it can be anything. If it is empty, if it's blank, that means it's not being used. So you can put anything you want. It can be food and bar. It can be whatever. So this is open. You can do whatever you want. And then path, again, so a full static path, or you can use environment variables. That's where you're going to start looking. Oh, no, sorry, I'm getting myself confused. This is a path that's going to be used for the key. So you can actually say, I want this DLL is in this path in program files. This is going to be part of the key. And then start location. And so this is where you actually start looking. Okay. So it will, if you want to start in program files, it'll start there. If you want to start in app data, it'll start there. And it'll just go through each item and then combine all those together for the key. Now, IP ranges, we support 24.16.8 max, okay? There's some examples there. So if you have a range, a fairly large subnet that you're attacking, you can use that. And also system time. We support a mask of either year, month, or up to the specific day. So, and during testing this, whenever a month changed and we thought all of our code was broken, we just realized that our system's working. So, all right, so it's time to do a demo, and hopefully it's better than this. So the scenario, there happens to be an American in Moscow, and their rubles just don't go as far as they did in Hawaii with dollars. And he really wants to play StarCraft. And you know, so he's gone to the underground, and he's using BitTorrent to get games. But in fact, there's a net out there attacking the current client of BitTorrent and backdooring hash or cracked games, right? So our first demo, we're going to use a one-time pad. We're using a specific build of BitTorrent, and we're going to be using an interpreter reverse HTTPS, and we're going to be loading a DLL in memory. And we're going to start looking at app data, and the code is going to be delivered through a cracked game, okay, that was patched with the backdoor factory to download and execute the payload. So there's a lot going on here. This is the idea. Cracked game gets downloaded over torrent, it runs a cracked game, and then our Ebola Go payload is launched, or is actually downloaded and executed. And then we have the in-memory execution of the HTTPS stage 1, which downloads the interpreter DLL over, and then establishes the command and control. So a lot of working parts. Let's go ahead and try to demo this. Great, let's see. Okay, there's our victim. Let's set up the demo. Now, I wrote some scripts to automate all this because I have shaky hands when I'm typing on stage. So this is our first demo, and we're just going to let everything run and then talk about it after it's done. All right. Oh. So what we have here is we're running Ebola. We're using a interpreter reverse HTTPS over 8443 DLL. All right, this is the first stage. And we have our config file. That's all we give it. And so you see here, we have, this is the payload length and hex. We're using, it tells us what we're using because that's what we put in the config file. And then we're using the BitTorrent as a pad, and we're using the maximum size, so 16 megabytes. Now, we have our test hash at 513 bytes in. That's the size of the payload. And then we have our byte width distribution, so it shows you matches across byte sizes. And so we actually have, we saved 468 bytes in compression. Now, and then we write it out. And I wrote a compile script because Go has a lot of flags if you're going to cross compile. So I have these compile scripts I wrote. And it outputs our demo.exe, and then we serve a web server, and then we just have a shell working here, or just waiting. So our victim is going to execute a cracked, backdoored StarCraft game.
This is after he's already downloaded it from BitTorrent.
Yeah. So it's working. So we should have a connection back here shortly. We just check to make sure. We got a connection. The demo gods have spoken. Damn demo gods. All right, let me refresh this. Are we being hacked right now? Somebody hacker. We're good. Yeah. We're having technical difficulties. All right. Yeah. Awesome. So yeah, it's really going well for us here. Hold on a second. It would be great if all our IP addresses changed like right before this demo. That's exactly what happened. Yeah. Awesome. So yeah, we're just going to crash and burn on all of our demos because of IP address changes. So what would happen here, it would actually execute in memory, and we'd get a connection back. No, it didn't help, because it was all internal on the VM. Yeah. So, all right. We're going to sort things out if you want to see a demo after this. Yeah, I apologize. But yeah, total crash and burn. So that was the first non-demo. The second uses all the same IP addresses, so it's going to fail, just as the first one did. So yeah, we definitely, demo gods rained down their hell and brimstone on us. So that's good. All right, so one of the things we have is, we were going to demo, was a layered payload. So the Bradley virus had several encrypted enclaves. And what we did is we put a stage 1 Python that wrote, we encrypted that, wrote a Go binary to disk as a stage 1, and then the Go binary executes in memory, and so you have multiple stages. Now, and that was actually, it took a little while, but it would have been a good demo. Fuck you guys. All right, so we have some known issues. Besides the demo. So launching Go from Go via memory module, you might as well just kill yourself. It doesn't really work that well. Launching PyInstaller inside of memory module, because you need to write something, you need to write stuff to disk for PyInstaller, it loses namespace. It's pretty hilarious. It doesn't even know where it's at. It's like, I don't know where I am. So trying to do Go PyInstaller, don't even try. So also doing PyInstaller with PyInstaller, that's the namespace issue. Also, Metasploit x86 PE.exe, the template that they use is so old that it just does not work with memory module. The x64 version works, but they just, it's like, it doesn't even work.
Yeah, the header's not right. So.
Yeah. So with our one-time pad, there is definitely a MZ header DOS leak. So you could actually say, all right, or is MZ anywhere at this location within any of the files on our network? So you can definitely try to find that. You might get a collision, who knows? So if you do this, this is okay. So Go executable, PyInstaller executable, and you can chain PyInstaller exe to Go exe. And so we're working on some things, C++ loaders, so we want to make a reflective DLL, so you can inject this directly in memory, and it will be a smaller footprint, because these Py and Go loaders are quite large. You're looking at minimum 3 and 4 megabytes before the payload. And then better chaining of payloads, so we want to be able to have many payloads inside of each other. So if we can get the C++ loaders working properly with the proper encryption, then you can just have reflective DLLs just injecting into each other. And then it's very easy, if you look at the code, it's very easy to transport this into OS X and Linux, right? So yeah, any questions?
Besides by the demo.
Yeah, we're gonna, if anybody wants to see, we can fix all that. What's that? Well, so, sorry.
Oh, yes, I am on the mic. Okay, so you know what? In the interest of time, do we have a question over there? It's probably better if we do questions at lunch. I have to be honest, because